It is 10 o'clock. I will get started with the session and have like about a minute for people to join until the actual first talk starts. My name is Hans Moritz Günther. I'm one of the co-chairs together with Rudy Montes, who chaired most of the sessions last week via the chairs. And we thank, as we said last year, we thank the SOC, we thank the speakers, we thank the people who helped us organize it. But in particular, I want to thank Rudy for the huge amount of work he's done, both as the co-chair of the SOC. He's done a lot more than I have. And he's also been chairing the LOC, whatever L in local means for a conference that's fully remote. So he's done a huge amount of work to prepare all this. And of course, he didn't say anything about that himself. So I want to take this opportunity to really thank Rudy for all the work that he has put in. We have a packed session again. This is session 7. It's going to last from 10 to 11:30. And the first talk is by Yuanyuan Su, who's going to talk about Chandra network analysis, Chandra imaging analysis using a technique that's called a convolutional neural network. This is an invited talk that lasts 30 minutes. And we're looking forward to get it started. So if you can share your slides, that would be great. And then go away.
Thanks, Maurice. Can you see my slide? Looks good.
Slides look good. So okay. Please go ahead.
Okay. Thanks for inviting me to speak here. And I really appreciate that the organizers can connect us all together from all over the world. Okay, so Chandra has been flying for more than 20 years now. And we know that one of Chandra's biggest advantage is its spatial resolution that is sharper than any other X-ray telescope. So Chandra observations have been greatly enriched our knowledge of high energy astrophysics. And so far Chandra has collected more than 20 trillion bytes of data. And it is desirable to find a way to maximize the scientific returns of such huge amount of data. Okay. And so today I'm going to present some of the applications of using convolutional neural network to analyze Chandra images. Okay, I'm going to take, so currently I'm teaching a machine learning course at my institute. And so I always tell my students that neural networks is nothing mystery. A structure is shown here. So the output of each layer will become the input of the next layer, and they are connected by the equation here. And if there's no F here, it's going to be a linear combination, and W and B are parameters to be determined. So once you add more layers, it's going to be a linear combination of a linear combination. It's never going to learn anything nonlinear. So to make it learn something more complicated, we add the activation function here. And the entire goal of training is to tweak the parameters until that you find that your prediction, the difference between your prediction and the true value becomes minimized. Okay, and the idea of convolutional neural networks has been around for decades and dates back to last century when David Hugo and Thorsten Wiesel, they have done a series of experiments on cats, and they inserted the microelectrons into the primary visual cortex of cats, and they realized something really interesting. When a cat sees an object, they don't really see the entire object directly or immediately. At first, they look at those really localized features, like look at the house, they look at the corners of the house and the door and the roof. Then only at a higher level, they put all those informations together, assemble them together, realize it's a house, not a fish, okay? And this inspired the birth of convolutional neural network. It is a network that concentrates on small low-level features and at lower levels, and then assemble them together at higher level, then make decisions. And Okay, and those layers are not fully connected. Okay. So makes the network more efficient and able to handle two-dimensional images. Okay. So the problem we are going to target on is how to recognize different populations of galaxy clusters. And there are two well-known populations of galaxy clusters, cool core and non-cool core. And this difference has been known for a long time. And I want to emphasize that the difference between cool core and non-cool core clusters has not only been recognized for nearby clusters, but you can also see them all the way to high redshift clusters. And despite that, this has been known for a long time. And the reason why some clusters are cool core and some are non-cool core is still super controversial. I would say the current prevailing theory is that major mergers may have disrupted cluster cool core and created non-cool core clusters, while those lasting cool core clusters, they have only experienced minor or off-axis mergers. Their core has never been disturbed. But then another also very popular alternative theory is that the difference is set by the physical conditions at cluster centers, perhaps a different level of thermal conduction and the power of AGN makes it determine whether a cluster is a cool core or non-cool core. There are also some other theory proposed that the difference was set even before the collapse of the clusters related to some kind of preheating. So cool core will be cool core forever and non-cool core will be non-cool core forever. We don't know the answer yet, but we believe the answer to this question is at the heart of cluster formation and evolution. So we're going to see whether a machine learning based approach is able to tell a cluster is a cool core or non-cool core. So first, let's define a cool core cluster. The legitimate definition is based on the cooling time defined here. You can see it depends on density, temperature, and metallicity. And we typically, in this field, we typically think that if the central cooling time is shorter than 1 gigayear, it's a cool core. If it's longer than 7.7 gigayear, it's a non-cool core. And the clusters between them, we typically call them weak cool core. So those divisions are for sure not strict, okay, but they are not super arbitrary because there are some physical motivations to choosing those numbers. And for clusters with a cooling time shorter than 1 gigayear, they tend to have multi-phase gas, which means that there may be it has triggered the thermally unstable cooling. And the 7.7 gigayear represent the look back time to redshift 1, that typically the time of the last major merger. Okay, so you can say that, okay, so this is how we classify clusters. Then we can just go ahead and measure cooling time, then we get the job done. But that's not easy. You can see to measure cooling time, you definitely need the spectral analysis. Okay. And especially it's super difficult to determine metallicity, which requires tons of photons. And even you have enough photons, you can see that to determine cooling time within very center, that's about 10 kiloparsec. Even with Chandra's resolution, you can only do it for very nearby clusters. Okay. And so even for nearby clusters with unlimited amount of exposure time, and it's still very challenging to determine cooling time because there are a lot of like projection effect, very, very hard to handle. There are some ways to deproject it, but those methods typically have some strong assumption. For example, you may have to assume that the cluster is spherical, or you have to assume that the outermost region of the study is truly the outermost region. There is no cluster emission beyond that. Those assumptions, I would say, probably not true in most cases. So it is the better way to determine a cluster is cool core or not cool core is that we can tell it from the images without using spectrum information. Okay. So we start our experiment using a mass selected galaxy cluster sample in illustrious TNG. And so we found like 300 clusters, then we made about 900 images. That's not a huge amount. And we make synthetic Chandra images for those clusters. We make the images as real as possible. Okay, we add all kinds of background noise and AGN contaminations. So Zhang Zuhao is going to give a talk later this week on how to use PAXIM and SOX tools to make synthetic X-ray images. And so we start with, we use those Chandra, synthetic Chandra images as an input to train a neural network. So here we use ResNet 18. The ResNet network has been around for like 60 years. So it's definitely not the cutting edge or state of art algorithm, but we think it's the one works best for this task because it consists of this we call it this residual block. You can see that it allows the information to be passed directly, like through those two convolution layer. It can also allow the information to be passed, skip it directly to this side and Zambol it together here. And so it provides a very flexible way to handle the data, and which is exactly what we need because we don't have a huge amount of data, only 900 images. That's really, really small amount. Okay, so let's look at the result. So this is the performance given by this deep learning method, and so we typically use F1 score or balanced accuracy, and you can see that it reaches a better performance than other traditional methods we typically use to determine whether a cluster is a cool core or non-cool core. You can also, but we didn't stop here, and it's true that we outperform traditional methods. But there's an even more important question is, based on what features, how did this deep learning algorithm determine whether a cluster is a cool core or not? Why it is able to outperform traditional methods? It must use some information that we didn't know about. Okay, so we use this technique called class activation mapping. And so essentially that it is able to highlight discriminative regions that is very informative, very important for decision making. And so as shown in those figures here, the top rows are like the input images we used, and the bottom rows are the corresponding cap mapping and maps. And you can see that the resolution is very poor. It's not going to tell us exactly specifically which features are important. So the brighter, the yellowish regions means it's more important, and the darker regions means it's less important. However, we can derive some profiles based on those maps. So we derived this CAM value radial profile for centered on the cluster center for cool core, non-cool core, and weak cool core clusters. And we've discovered something really interesting. So whether a cluster is a cool core or not depends on the cooling time that is only defined within the very center. Okay. So it's not surprising that the central region, the innermost region, is the most useful region. But in addition to that, the network thinks that regions outside the cluster center is also super useful, especially for non-cool core clusters. You can see those profiles extended out to a few kiloparsec. And so it has used informations outside the cool core where it's not related to the definition of the cool core to determine the cluster is a cool core or not. And even more interesting, I want to emphasize that, remember, our method has outperformed the approximation made by central density. From the definition of cooling time, you can see that it's highly related to density. And from an imaging point of view, the most information you can get from image is density, right? And but it has outperformed the density. So it used some features that is not related to density, but more directly related to cooling time. And those features are likely to be outside the core core. So perhaps it has used some agent feedback related features like cavities to determine the power of feedback, or it has recognized some features related to disruptive major mergers. We don't know exactly because the resolution of this TAM is so poor. And so it's really, really important to interpret networks. Otherwise, it's just a black box. Even it outperforms the traditional methods, it's not that meaningful. So there are a couple of commonly used interpretation methods, and some of them are more complicated, some of them are more straightforward, and some of them are gradient based, some of them are like heat map based. So I have to say that a lot of times, even after you have visualized the networks, it's still very, very confusing. Like sometimes you feel like you have to interpret the interpretation. So at this point, I got some help from my junior collaborator. Okay, when I was working on this project, my junior collaborator was like 15 months, and she just started to learn how to talk. She couldn't talk, but she can say a few words. And so I sometimes like babies and AI, they are like really similar. You know that they are super smart, but they couldn't communicate with you directly. So at that time, she could recognize dogs and cats. And when she see a dog, she say dog. When she see a cat, she say cat. And she's very accurate. The performance is very good, but I have no idea based on what features she is able to make the decision. Now, until one day, I read her a book, and there is a baby seal, a picture of baby seal in that book. And she saw this baby seal. She pointed at it and says, cat. Then it makes me realize that the reason she is able to identify cat is not because she used the feature of like ear or tail or legs. She has been using this whiskers to recognize cat. And that's really, really inspiring. So I also want to emphasize that I know that these days machine AI may have outperformed human beings in many tasks, but human beings are really unique. Like if you show a baby an apple, just one apple, they are able to generalize it to all the apples in the world. You don't need a huge amount of data to train them. And also it without saying that human beings can do multitasks, but AI usually couldn't. And you don't need to apply any cost function to train them. Like whenever she see a picture of Mulan, and she always call it mommy, and I never corrected her. But they can see that she has been using this like probably the long dark hair to recognize me. So the idea is if we can find something in common between misidentified cases and the correct cases, that may be the feature that the algorithm has used to make decisions. So we try to look for misidentified cases in our study. But we want to choose those that are confidently misidentified, because if they are not confidently misidentified, like it's not so sure anyway, so it's not surprising that it's a mistake. So luckily for the classification task, there is usually a measure of confidence comes with it, because most classification algorithm will predict the probability for each class. Then it will choose the one gives the highest probability as the decision. Okay, so so we find those that are confidently misidentified cases. And among them, I find one particularly interesting in this one. It has a cooling time of 4 gigayear. It's a weak quark cluster, but the network thinks it's a non-quark cluster, and it has recognized that it's a merging cluster based on CAM. You can see it captured this subcluster here. So maybe it has found some association between merging and non-quark, and I find this really interesting. Okay, and so this work has been published at MNRAS. So please check it out if you want to find more details. And okay, next, I want to look forward a little bit. So machine learning has been widely used to solve a lot of astrophysics problems, but so far I have to say most studies have been like ours have been using simulation data for training and testing. There's a huge gap to apply machine learning to real observations because there are some really serious difficulties. First of all, in real observations, you don't know the ground truth. For example, you want to train a network to predict cluster mass. Even you use weak lensing mass, that still involve a lot of known and unknown biases. You never know what's the true mass of the cluster. Also, it may not be difficult to find large data sets, but it's very difficult to find large data sets with labels. Okay, and lastly, there are always noise and background. Some of them we understand, some of them we don't even know how to describe them. So my group has made some attempts to try to apply CNN to real observations, and as a prototype study. So this study is led by my students, Shengjie Lin and Tony Liang, and they have their goal is to our goal is to obtain relatively accurate cluster mass for a large number of clusters. So we collected a large number of clusters from SDSS, like 25,000 clusters. That's a huge amount. And we always have their optical images in 5 bands, U, G, R, I, Z, and we don't know their mass. But for a very small amount of them, like 1,500 clusters, we can get some relatively accurate mass estimates based on X-ray and SZ observations. Okay, so then we need to find a clever approach to utilize both data sets. So we use this transferring learning. It's a 2-step architecture. You can see the first step, and we train the network to predict which band are those images. Like, are they G band, are they U band, are they I band? So it's a 5-class classification. Then we train it with this huge data set. Then we take the lower level of this architecture and apply to
2.5 minutes.
Oh, okay, thank you. To this smaller data sets, we have relatively accurate mass estimate. Then we are able to predict the mass of the clusters. So I'm going to show the result that it's a huge scatter between the prediction and the ground truth. It's not beautiful, but this is a real world. And I have to say our results start to rival the performance rate mapper. That is a state-of-art algorithm to predict cluster mass from optical images. And so just to just to look forward a little bit, and very soon that there are going to be multi-wavelengths large cluster surveys, not only from optical images, but also from SZ and X-ray studies. And so with the coming of flood of data, and the performance of our algorithm is very likely to improve, but the performance of rate mapper is probably not going to improve much. So despite that, there remains a huge scatter in the performance of this current work. We expect that it may become better soon. Okay, thank you. I'm happy to take questions.
Yeah, there are already a couple of questions. If you have any more, please type them in the Slack, and I'll read them out to the speaker. The Slack talk discussion channel. You can also put them in the Q&A, but the Slack is easier because then they stay around and the discussion can continue after the Zoom session is closed. So in the Zoom session, we have a question from Jeff Scargill. He asked he lists a number of things that I'll read out in a second, and asked, in your neural network application, do any of those cause any practical problems for you? In particular, like the uncertain convergence, that you don't know if it converges versus a local or global minimum. It depends on the initial state and may also depend on the structure of the network that you choose. I mean, there's a lot of choices involved, and which of those, if any, cause practical problems for the application that you're pursuing.
Mm-hmm. Thank you. So I would say we didn't deal with all those questions you brought up, but we did some tests on different networks. So like we tried a few simpler ones and some more complicated ones, but I would say this one gives the best performance so far.
Juan Martinez Galacera asks or comments as a comment and says, you select objects that are misclassified by your neural network, and that way you're finding anomalies. He suggested you're probably finding anomalies. So the question is, could you perhaps use this as an anomaly detection approach to find in real observations, to find objects that are really interesting because they're not what you expect them to be?
That's a good point. First of all, it depends on ideally if we are able to truly apply to real observations, then I think that that could be a very clever way to find an interesting object. So the bottom line is you think that misidentified cases are like some mistake, right? It's a bad thing, but it's not. It's maybe the most interesting thing.
I have a more technical question to your method. Since you learn on the images, like the orientation of the images may matter. There's really the orientation that Chandra has on sky at the time of the observation is random or arbitrary. Do you take that in account in the training in some way? How do you do that? Or how do you deal with that?
We want to tell the network that the orientation doesn't matter. The cluster doesn't become a non-cool after you rotate it. Same as when you recognize a picture of a dog, and once you rotate it, it's still a dog, it won't become a cat. So when we train the network, we randomly rotate each input images. So the network knows that the rotation won't make a difference.
Are there any other questions that people want to raise? I don't see anyone typing. And we have about 30 seconds left. So thank you very much for the interesting talk. I specifically enjoyed the way you explained all the steps in the process. That is for techniques like convolution, like these networks, they're still fairly young. I think it's very important or very useful for many of us who haven't done that ourselves. Like I've read about it, I've never used one. So I appreciate you telling us how we actually get that.
Yeah, it's not a mystery. Yeah, thank you.
I would thank you for talking, and I would like the next speaker, Tong Bao, to share his slides and to get started then.
Can you see my slides now?
We can see your slides, but they're not in presenter mode yet. Now it looks good, and we can hear you. So please go ahead.
So thanks a lot for the organizers. It's a great honor to be here. I'm Tong Bao from Nanjing University, and my course is Juan. Today I will introduce my recent work searching for quasi-periodic oscillations in active galactic nuclei of the Chandra diffuse source. I will start from the background why QPO matters and what can we obtain from the QPO searching procedure and with some simulation work. So first, let's see some examples of QPOs. We know that they are discovered in black hole binaries, ultraluminous X-ray sources, and active galactic nucleus. The exact origin of them are still not established yet, but we believe they are probably associated to disk instabilities, geometrical effects like disk precession or Kepler motion near the its core. So generally speaking, it should be caused by some geometrical or dynamical effects of the inner edge of the accretion disk. So this statement stands thanks to the approximate relation between QPO frequency and black hole mass, like I show in this figure. Black hole mass would be ranging from 10 solar mass to 10^8 solar mass. So here we present the first dedicated search for agent QPOs in the deep field. So deep server is like Chandra diffuse source provided as an advantage of a nearly unbiased sample of hundreds of agents at the same time. We divided the total 7 million seconds into 4 epochs. And then we apply the well-known normalized Lamb-Skagel method into all the sources, like nearly 1,000 sources and the 4 epochs. But we found no significant joining periodic signals among these. We said joining periodic signals because actually we can see that there are dozens of them are valid detections over 3 sigma significance. Here FAP means false alarm probability. But the dashed line level here represents the Chandra dizzying motion period. If I remember right, it should be 700 and 1,000 seconds for respectively. But this two labeled by number is actually caused by a strong outburst at the short time scale. So both of these two types are not genuine QPOs from the agent itself. But still, actually, we can give an estimation on the occurrence rate of persistent QPOs, since we can simulate the agent light curve with or without QPO variation. And based on the large number of the simulated light curve, the detection efficiency of the searching procedure can be estimated by, here we use 1,000 fact light curves for each group of dataset. And we can barely see the QPO detection efficiency has dependence on the source count rate, the X level, and the quasi period, and the different QPO model. Model A and model B represents the detailed model about their quality factor and advanced magnitude. I would not elaborate further in this talk.
2 minutes.
Okay, thank you. From this equation, we have the detection efficiency and the Chandra diffuse source sample. And also we know that we have 0 event of QPO detection. So the occurrence rate of QPO should be constrained to be lower than about 15 to 20%. Okay, finally, I'll give a summary here. No statistically significant QPO is found on any of these 4 epochs, and the intrinsic occurrence rate is constrained to be lower than 20%. And finally, the last point I should present is that despite we have 0 detection of persistent QPO, that means lasted for at least 1 total epoch, we divided all the light curves into small subsets, and we found 2 short-lived QPO candidates. Okay, that's all. Thank you. I'm happy to have any questions.
We have almost a minute for questions. Okay. So one of the questions we have is by the Skagel. Yeah. Do your false alarm probabilities account for the colored, not the white noise, but the colored noise background on which you have below your QPOs?
Yeah, I understand what you mean. Here we have we should have the agent light curves red noise because we know their observation gap. Here we use the false alarm probability from the bootstrapping method. So I think they should already, I think they should be already considered in the bootstrapping process.
Thank you. I think that answers the question. Thank you so much for your talk. If there's any more questions, please put them in the Slack channel, and we'll continue to our next speaker, Hugo Tranin, and I'll give you after 15 minutes. I give you a 2-minute warning.
Okay, so
I'm not seeing anything yet. Now there are the slides, and I hear you. So please go ahead.
Thanks. So hello everyone, and thanks for inviting me to present the work I'm doing for my PhD. So I am Hugo Tranin, second year PhD student in IRAP in Toulouse in France. And today I will show you 2 classification approaches we developed to mine large fractions of the Swift and XMM catalogs, but that will soon be applied to the Chandra catalog. So to this day, X-ray catalogs gather about 1 million X-ray sources, and most of them remain unstudied, as you all know. But this number is going to increase a lot very soon, considering the 30,000 sources observed by Rosita in just 140 square degrees. So, and in the X-ray zoo, you expect a majority of AGN, then stars and X-ray binaries, and then some more exotic objects like tidal disruption events, ultraluminous and hyperluminous X-ray sources, and special types of AGN and so on. So a lot of treasures are hidden in those catalogs. And that's part of the reasons why it is useful to classify them. But first, we have to wonder which features, which data are needed if we want to classify them manually. For example, this object is a typical AGN, and I can tell you so because of all these reasons. The source location, the X-ray spectrum, the X-ray light curve on the short term and the long term between different observations, and the multi-wavelength counterparts are all important in this task. And you have about 55% of the XMM and the Swift catalogs satisfying enough criteria to be classified this way. But how can you automatize the classification? Well, I found in some first approaches in the literature, and they were always on small samples. For example, Dacheng Lin and collaborators in 2012 classified, used the decision tree to separate 3 classes, that is stars, compact objects, and AGN. And later works used the random forest method, which is more accurate, but less interpretable. So if I sum up, I can say that very few classification schemes are probabilistic, and most of them only use limited datasets, both in size and in features. Plus, their training samples contain few X-ray binaries and cataclysmic variables. Okay, so the question is, can we do better? For our sample, keeping most of the Swift and XMM catalog, we identified a training sample for these 4 classes: AGN, stars, X-ray binaries, and cataclysmic variable. And then we also identified optical and infrared counterparts. And last but not least, we gathered X-ray detections from different observatories to better access the long-term viability, as illustrated here. Okay, so now that we have an enhanced catalog, let's look at the distributions of some features. For example, you see here the densities for the stars and the AGN of the X-ray over infrared flux ratio. So you can, well, from the training sample, sorry. You can say, okay, all sources below -1.5, for example, are stars, and all other are AGN. But this is not very accurate because there is an overlap here. So one improvement is to infer the likelihood of a value given each class. So for example, if your source is 100 times fainter in the X-ray than in the infrared, then the likelihood of the stellar class is 93%. And then you can combine it with another data, say the galactic latitude, do the math with the Bayes rule, and obtain the posterior probability of your class. And what we just built is called a naive Bayes classifier. Sorry. So, all right. So in practice, we used not 2, but about 15 features. And for each category of feature, for each category of features, that is the multivariate counterpart, the variability, the spectrum, and the location, we assigned a weight here in the final formula. Then we were able to optimize these coefficients in order to obtain the best results for the class of our choice. And here, that is the X-ray binaries. So in a nutshell, we are left with this flow chart of the classification. You start with a training sample, you estimate its densities, you optimize some coefficients, and then you can apply the classifier to the whole sample. And it's time to look at some results. Starting with this slide. So beginning with the training sample, here is the confusion matrix of the classifier. And as you can see, AGN and stars are very well retrieved, over 99% of them, with a very good precision. And X-ray binaries show good results as well, thanks to our optimization. But that's not quite the case for cataclysmic variable. And also we compared our results with the results of a more standard random forest method, and we got a similar performance. But as we saw last week in a classification work, being able to interpret the results is as important as reaching an apparently good performance. And the good thing with our method is that for any source, you can very easily retrieve the reasons why it was classified as it was classified. So indeed, another classification product is this plot, showing the probability track, that is to say, the contribution of each property to the final probability of each class. So for example, you can see that this source was classified as X-ray binary because of its variability and also because of its hardness. So moving on to the test sample, we obtained above 75 AGN of our sources classified as, well, above 75% of our sources were classified as AGN. That's more than 250,000 AGN candidates, and 20% of stars and something like 8,000 X-ray binaries. So we verified manually the classification of 200 sources, and the classification as stars and AGN was more than 90% accurate. That's not the case for X-ray binaries and cataclysmic variable. And sorry, I have some trouble with my slides. That's not the case for X-ray binaries and cataclysmic variable, and this is because of two main reasons. Many false positives are special types of AGN and stars, like young stellar objects or very variable stars, and they are thus different than the bulk of stars and misclassified. And also, there are only a few hundred X-ray binaries and cataclysmic variable in the training sample, which may not be enough, considering their very diverse nature. So the third result I wanted to show you is about the outliers, and we implemented an outlier measure, some kind of an anomaly detection method. And it is based on the densities of the training sample still. To be simple, the lower the density of the sources at a given point of the parameter space, the higher the outlier measure. And this proved useful to isolate some special types of AGN, as you can see here, but also stars, but also to spot spurious sources and a small number of treasures, I mean rare and exotic objects such as tidal disruption events, supernovae, and so on. Okay, so now let's step back and have a look at what we achieved in comparison to the works I showed you earlier. So our sample is probably enhanced. Our classification is probabilistic, interpretable, and applicable to a large number of sources, but it is still limited by the training sample of X-ray binaries and cataclysmic variable. So my final slides are about a project we developed to overcome this issue, and this second approach made use of citizen science. So as you already know, citizen science is used in astronomy since 2007 with a website called Galaxy Zoo, which was designed for the morphological classification of galaxies. And it was a tremendous success. So not only the wisdom of crowds led to a reliable classification of about 1 million galaxies, but also some volunteers made serendipitous discoveries, like a new class of compact galaxies shown here and called the green peas. And now their classification are used in the training samples of many machine learning experiments. But in X-ray astronomy, citizen science has never been used, to my knowledge. So we developed a website called Klaxon, on which every volunteer can learn how to classify X-ray sources and actually enjoy it, hopefully. And so far, we've got about 50 users, and and they did more than 50,000 classifications. So to ensure the reliability of the results, they are first trained on known objects, and only after reaching a certain success rate, they can classify unknown sources. And we show each object about to at least 20 people to make use of the wisdom of crowds. And so this process will ensure the reliability of the experiment. And our belief is that such a citizen science experiment can be a very useful complement to machine learning when you need to enlarge your training sample. For example, as of today, we obtained about 15 new X-ray binaries candidates and some possibly new cataclysmic variables. But I would like to save time for questions, so I leave you with my take-home messages. So our code, Klaxboy, is an efficient, probabilistic, and interpretable and general-purpose classifier of X-ray sources. AGN and stars are very efficiently retrieved. X-ray binaries show encouraging results, but may require a bigger training sample. And future X-ray surveys will be a real reservoir of exotic objects that will need such a classification to be found and studied. And last but not least, we can develop some synergies between machine learning and citizen science to make the most of our beloved catalogs. So I thank you very much for your attention, and I will be very happy to take any question.
Thanks a lot. There are a number of questions already, and I'll squeeze in my one first. You talked a lot about the importance of the training sample, and you said what you're going to do to improve it. Where does your current training sample come from?
Yeah, my current training sample comes from, I don't have a slide to show it, but different catalogs of known AGN and stars. So for example, the Veron and Veracity catalog of quasars and AGN, the catalogs of AGN from the WISE selection technique, so mid-infrared selection technique. And also for stars, we made use of, well, general catalogs of known stars like Hipparcos and the Oskai catalog of stars. And for X-ray binaries, it's, well, for X-ray binaries and cataclysmic variable, it's something like a dozen of catalogs from the literature identified during specific pointings and surveys. I hope that answers your question.
Thanks a lot. Yeah. Christian Schneider has a question on the Slack that came in first, so I'll ask it first. He says, can you expand on the achieved accuracy and completeness? On one slide, your number suggests that you are 99% accurate for AGN and stars, and then the manual inspection says something about 90%. How are these numbers estimated, or how they're calibrated?
Yeah, okay, so that is the results on the training sample. So these objects are already labeled, and they are already well known. So they represent well, a kind of brighter sources. Well, what I want to say is that the training sample and the test sample have differing properties because the training sample is made of already known objects, and the test sample is usually fainter objects with less detections. So this explains most of the difference in recall and precision here. And the manual inspection was done by me and by and confirmed by my supervisors. So on these handful of sources. So this explains the difference, and also the two challenges I explained earlier.
Thank you. Another question by Mara Salvato asked in the Zoom, and says, thanks for the talk, Hugo. One question and one comment. The question is, you're already assuming to know the correct counterpart for the X-ray source in the other catalogs. How do you do that?
Yeah. At first, we used only a very basic correlation technique, just looking at the angular separation between the two, and ensuring that it's below the pre-sigma X-ray position error. And then we used a more more fancy tool to do that, which is NWay, which was developed by Salvato and collaborators. And this, maybe this is enough to answer your question.
I think that sounds very good. Yeah, if not, I copy and paste all the Zoom questions into the Slack so the discussion can continue there after the talk is over. Pavan Ahaba asks, what parameters do you think are the most important ones in the classification?
The most important parameters?
Yeah.
Okay.
Like you put a number of parameters in, which ones turn out to be, you gave one example where that is example, but in general, which ones turn out to be the most important ones?
Well, in general, X-ray, well, because we optimized our classification on the X-ray binary class, my answer will focus on the X-ray binaries, and the features we used are shown here. Well, there are more than this list, but what we found is the variability features. So, for example, the ratio between the maximum and minimum flux, both inside an observation and between observations, proved very useful to label the source, to classify the source. And actually, the weights the weights obtained by the optimization show the quantitatively the difference between the different feature importance. So the variability is important, but also the multi-wavelength counterparts. And after them comes the hardness and location, except for the location in the galaxy, which is not still unclear.
Thank you. There's a number of other, there's a number, I've gone over some comments and there's open questions left in the Slack. So it'd be great if you guys can get back to that, if the discussion can continue there. Unfortunately, we'll have to move on to the next talk. Thank you for leaving so much time for discussion. I think that's really useful. And we still didn't get through all of them. So I would like to ask the next speaker to share her slides, which is Serena, and she is going to talk to us about BA X-ray binaries. And so we see your slides, not yet in presenter mode, but they're there. And so please go ahead when you're ready.
Yeah, thank you. Okay.
Looks good now.
Perfect. Thanks to organizer, first of all, for having given me the opportunity to talk about my BX binary project. I would also like to thank all the people listed here who are my collaborators on this project. And yeah, so I will be talking about BX binaries in the Small Magellanic Cloud as indicators of mass transfer efficiency. And if you like to check out, to know more about this project, please feel free to check out our paper here. And if you have any questions, you can feel free to contact me on both on Slack or on this email address here. So the main goal of the project is to try to learn something about binary evolution by comparing observation with predictions. And the first question, of course, is why should we care about binary evolution? And well, binaries are really an important topic in astrophysics, whether you're doing, you're studying gravitational waves, massive stars, or even chemical abundances in galaxy evolution. It is by now clear that you need to account for the effect of stars being in multiple systems. Unfortunately, though, there are still a lot of uncertainties in binary evolution, and here I just listed some of them. So to tackle some of these uncertainties, we decided to focus on a specific population of systems, and in particularly the BX binaries. And to tell you what BX binaries are, let me start by saying what are BE stars. So BE stars are hot main sequence stars, which are rapidly rotating. And this rapid rotation, in combination with other effects, determines the formation of an accretion disk that we can detect. And so BX binaries are therefore high mass X-ray binaries composed by a BE star and a compact object, which is accreting from the decretion disk of the BE star, and in this way emitting the X-ray that we observe. And when the compact object has been identified, usually the nature of the compact object has been identified to be as a neutron star. And as I mentioned before, so we are trying to learn something about binary evolution by doing this comparison between simulation and observation. And in practice, this means trying to answer the question, can we understand the main properties of the observed BX binaries? And yeah, so again, we need this comparison between a synthetic population of BX binaries and unobserved ones. And in particular, in this project, we focus to the observed population presented in the catalog by Cohen-Kirk 2015, which includes the information about 69 BX binaries, including neutron stars, which have been detected through observation by different instruments, including Chandra. And actually, Chandra has been really giving an important contribution to this catalog, as it allowed to detect some of the widest systems that were present in the catalog. And we are comparing this observed population with a predicted one, which comes from the population synthesis code COMPASS. And if you can think of population synthesis code as black boxes where we can put our approximated understanding of binary evolution plus some assumption and simplifications. And so the study seems to indicate that most of the BX binaries have experienced a stable phase of mass transfer. So this is what is the suggested typical formation channel. So the most massive stars of the binaries will expand quicker and fill its Roche lobe. The Roche lobe is the region around the star where the matter is gravitationally bonded to the star. And when this happens, some of the matter will be lost by the star, which we call the donor, and may or may not be accreted by the companion star, which we call the accretor. And then this initially most massive star will end its life as a neutron star, which will be in a system with a B star. And so the typical timescales of this stable mass transfer phase are enough to allow a considerable mass to be transferred from the donor to the accretor. And this fraction of mass which has been transferred is what we call the accretion efficiency, and is here represented by this beta parameter. And what we find is that this fraction is actually higher than previously thought, and that actually most of this mass transfer should be quite conservative. And of course, actually the story is much more complicated than this. And so this is indeed, so on the right here, you see a list of observable that would be very useful for us to constrain our models and be able to learn even more on binary evolution through this observation of big binaries. And let me just conclude by saying the last point is that we found is that we can explain the abundance of big binary in the small Magellanic Cloud through the peak of the star formation together in combination with low angular momentum losses. And this point actually inspired a Chandra proposal, which is called testing the age hypothesis for big binaries, which has been recently approved, recommended for the Chandra program by the stage 1 panel review. And with this, I'll thank you for your attention. And please, if you have any question, contact me on the Slack or again at the email address. Thanks.
Yep, thanks a lot for your talk. I'm looking forward to see what the observations will show when they come in. We are through the 5 minutes, so any discussion will have to happen on Slack. And I would ask the last speaker of the session, Víctor, to bring up his slides and get started. We see your slides. They're not yet in presenter view, but I see you're working on it. Looks good. Okay. So please go ahead.
Thank you, Moritz. Well, it is a pleasure to be here with you all. I'm Samuel Pérez. I am an applied mathematics and computer science student at the Universidad Rosario in Bogotá, Colombia. And today I'm going to present to you the project that we are doing for my undergraduate thesis, which is called Unsupervised Machine Learning for the Classification of Astrophysical X-ray Sources. And this project has been supervised by Rafael Martínez Galarza from the Center for Astrophysics and Alexander Caicedo Dorado from Universidad Rosario. Thank you to the organizing committee. It is a great pleasure to be here, and I'm very happy to present the work with you all. So let's start talking about a little bit about the challenges of classification. So we have seen some serious efforts and very successful efforts on providing an unsupervised learning pipeline for the classification of X-ray sources. Though when using supervised learning, we have many challenges to overcome, as many authors have said. For example, one of them is the lack of optical counterparts. But when we have them, as you may see in this example at the right, where we have the optical magnitudes versus the fluxes in X-rays, we could see that we could separate the classes. Actually, we could identify very good them. But even though that we have optical counterparts and we have classes here, we can find an overlap between those classes. So that's another challenge from the supervised classification. First, we have the lack of optical counterparts, but then when we have the optical counterparts, we could find some overlaps that we want to overcome. Other challenges of classification too is that we have, of those with optical classification, there is a significant imbalance between classes. And as we have seen, for example, with the George Washington University group that have been doing an amazing job in providing a pipeline for supervised classification, they have said, though, that we have this particular challenge to overcome, that is that we have many classes underrepresented in the dataset. And for example, here we have more than 1,000 AGNs, but less than 100 low mass X-ray binaries of neutron stars. So those are that is a great imbalance, and that is a challenge to overcome in the supervised classification. And that is actually our motivation that for the work that we are presenting here, a new approach of that classification. So we have seen that it is hard to classify sources in the X-ray catalogs, right? Yet we want to do it, of course, and we have seen many efforts here in the conference. Because classification of serendipity sources detected in X-ray catalogs is very important to pinpoint exotic phenomena such as GRB afterglows, stellar flares, luminous X-ray binaries, obscure AGNs, etc. So many of the sources, as we know, of the catalog of the catalogs of X-rays have not been classified or studied in detail. That's a clear motivation for classify as many catalog sources. In this case, particularly, we are working with the Chandra source catalog as possible, both on the galactic plane and outside the galactic plane. So our approach in this case, following the motivation that I presented you before, is to use unsupervised machine learning. So we have several questions here. So given the challenges of supervised classification that I presented to you, can an unsupervised approach be used instead? Another question is that to what extent we could use just the X-ray information from the catalogs, in this case, the Chandra source catalog. How could we use that and can be used to provide a probabilistic classification of Chandra source catalog, in this case, sources. And this is part of the ongoing work, but this is an important question too that we want to answer, is that to what extent does optical information improve classification accuracy? So we say challenge accepted to this important task. Fortunately, we do have several wonderful catalogs of serendipity sources, such as the Chandra source catalog, such as the XMN catalog, and soon we will have the Rosita catalog of sources, which will cover all the sky. So that's very important. The efforts that we are doing here right now with the catalogs that we have will be very important for the science of the future with Rosita catalog. Okay, so I introduced you the project, and I want now to talk about the data that we are using. And the data that we are using is the Chandra source catalog, as I said, and this is one of the most important X-ray sources catalog, which covers more than 300,000 unique compact and extended X-ray sources in the sky, and we have more than 900,000 individual observation detections. And with those observation detections, we have many properties. For example, photometrical properties, the one we have here, and we have spectroscopic properties too, such as the hardness ratios, and we have intra and inter observation variability measures. And of those measurements that we have, we could extract them from stack detection the stack detection basically covers many images in the same region in the sky before we detect the per-observation detection for each sources. So with that, the stack detections, we could extract larger scale variability information because we could observe how a particular source could vary in the different observations that we are stacking. But we have, if we want to have a shorter scale variability information, we could go directly to the per-observation detection. And here I show you a little bit of like a summary of the hierarchy of the Chandra source catalog. And in particular, when we have a particular observation detections, here I show you a plan of the X-ray luminosity versus the variability time scale. Mostly the typical duration of the Chandra source catalog fall in this range that you see here in this black rectangle, which is mostly on 5,000 to 50,000 seconds in lifetime. And if you can see here in the lifetime, in that tiny scale, we could find many kind of sources like Pérez, X-ray binaries, AGNs, GRB afterglows, etc. So it is very important, and that's why we are using here the per-observation detections. For a project, we are going to use the per-observation detection because even though we are in a short scale variability term, we can find many kind of sources. Okay, so now I'm going to present you the pipeline that we are using in our project. I'm going to follow each of these boxes. So first of all, we did a data acquisition over the Chandra source catalog. Then, after having the data needed for the project, we will do a normalization or a log transfer and normalization for some of the properties. Most of the properties have to be normalized because, as you may know, some properties represent variabilities, probabilities, some others represent extents. So we have different scales here. And a log transformation is needed for other sources that have extreme values and that we want to skip the skewness of the properties of the data. So after that we have normalized the data, we can apply an unsupervised machine learning algorithm. And after that we have used the unsupervised method, we could analyze these clusters by statistical knowledge by seeing how the clusters are performing and what they are separated. Like if the clusters are separating the sources by their properties, for example. After that, we have analyzed those clusters and find out that we have a very interesting separation of the sources. We could cross match those sources with SIMBAD in order to extract the types that we need for our approach for the classification. After that, we have the types of the classes. We could analyze how those classes are distributed in each cluster. And we could find, for example, predominant classes in one cluster and predominant other classes in other clusters. So after that, we have that, we could assign a type to sources that did not find any type in SIMBAD or found like an ambiguous type. And we could do that by similarity analysis, which is based in distances. Okay, so I'm going to talk about a little bit about the data that we use and the properties that we use. Actually, as you may see here, we use mostly properties related with variability, and in this case, we use properties related to the spectroscopic measurements. For example, the hardness ratios. We use properties related to the strength, such as the source area, related to the temperatures, such as BBKT, related. Those are very important for the variability, the intra-observation variability. We have many properties and features of those properties, like the standard deviation, the mean value, the maximums, the minimums. So these are the properties that we use in our work. And when we see a particular projection of that property space, for example, here we have the hardness ratios between the medium and soft band, and the hardness ratios between the hard and medium band. And we have color coded the sources by the variability probability in the broad band, in the hard band. And you could see, for example, here that we have a correlation, like a kind of a correlation, a functional relation between those variables and those particular properties. As you may see here, for example, in this particular part of the graph, we have low variability sources, but if we go to the top, we can find very variable sources equally to the bottom of this graph. So we want to understand then and exploit those differences and exploit those relations between the properties to have a better classification with an unsupervised machine learning approach. So what we use in our pipeline are these two methods, basically the k-means clustering algorithm and the Gaussian mixture models. And we are going to start with the k-means algorithm, as you may see here in this GIF. Well, the k-means algorithm is one of the most important, or one of the most known unsupervised machine learning algorithms. First of all, for the k-means iteration, we have to specify how many clusters that we want in our model. For example, here we have 4, and that's actually the value of k. And we have to initialize the centroids, which are represented here by the x crosses, the y crosses here. When we initialize those centroids, we are going to assign every point of the data set to their closest centroid by the Euclidean distance. And after that, we have assigned every cluster, every point to a cluster. We could redefine the new centroids by performing a mean between each cluster. So that's what we are seeing here until the convergence. So after we perform a k-means algorithm, and after we decided some parameters, for example, the number of clusters by empirical knowledge, because we for example, in here, we are using k equals 6, and that's because by doing many experiments, we found out that this separation gave us an interesting characterization of, for example, you could see here in the left graph, you could see that the sources in the galactic in the galactic plane are separating from the sources outside the galactic plane. So we could find that even though that those are separating, that those are different clusters from the outside out of the galactic plane, we could find that we have many clusters too, many clusters represented in the galactic plane. And we could see that that separation of the properties in the clustering by looking again at the hardness ratios. As you can see here, the hardness ratio in the medium and soft band, and the hardness ratio of the hard and medium bands. And we could see that, for example, some of the clusters tend to be very hard, and some of the clusters tend to be very soft or be in the medium band. So that's interesting. We are seeing a clear separation of the properties. But when we K-means, we have a lack of flexibility in cluster shape. Since we assume when we are doing K-means, we assume that we have spherical shaped clusters. And additional to that, we have a lack of probabilistic cluster assignment because we are performing a hard clustering technique. So we decided to migrate the analysis to a more scalable approach, which is the Gaussian mixture model that is more flexible and more general than the K-means algorithm. And the Gaussian mixture models are actually very related to the K-means algorithm. Since, for example, we could say that the K-means algorithm is a particular case of the Gaussian mixture models. And for example, here we are not assuming that we have spherical shaped clusters, but we are assuming that all clusters are distributed by a Gaussian, but we don't know the parameters of those of that Gaussians yet. So for finding those parameters, we are going to use a very known algorithm called as expectation maximization, which is gonna maximize the log likelihood to find those parameters and to finally fit those Gaussians to a interesting cluster, as you can see here, until convergence, of course. And as you may see here, we have a plot again of the hardness ratios between the hard and soft band and the hard and medium band. And as you may see, the algorithm actually tries to separate the clusters according to their X-ray hardness ratios. And for example, you can see the stars are representing the centroids of each cluster, and we could see a clear separation again of those clusters.
2 minutes.
Thank you. We could see that again. We could see that again in this separation of the clusters. For example, we have very soft clusters, and we have, for example, very variable clusters too, and we have very clusters that are very low variable. So that is interesting because that is saying to us that the separation of the clusters is not coming by magic, but they are coming by a clear separation of the properties. So after that, we cross-matched the clusters with SIMBAT, actually the sources, all of the sources that we had in the data set with SIMBAT, and we cross-matched with that with SIMBAT in the sake of the classes of already clusterized data. So after performing that cross-matching, we found out that approximately 44% of the data didn't find an unambiguous or any match at all. So we have a lot to do, almost the half of the entire data set. And when we have done that cross-matching, we could find that we have some sources that are very dominated by, for example, Orion B stars or YSOs or T Tauri stars that are joint stars, and other clusters, for example, the cluster 5 dominated by Seyfert 2 galaxies. But in those clusters, we have a lot of sources that didn't find any matching type. So those sources and the ambiguous ones, like the stars or X-ray source, we want to classify by doing a similarity analysis. So we have those source observations that did not find any ambiguous class in the SIMBAT cross-match. How do we classify them? So we are performing distances here. By performing distances, what we want to do is to use the Mahalanobis distance, and that's because it gives us information. This Mahalanobis distance gives us information about the correlation of the point that we are trying to find the distance and the distribution of the subset that we are looking for. So for example, here you could find that these points are in the same Euclidean distance, but the blue points are actually closer because they are correlated with the distribution. And after that, we want to do Mahalanobis distance between the subsets in each cluster. This is a particular case of a cluster. So we have YSOs, T Tauri stars, BY Dragonis stars. And first, we want to compute the mean Mahalanobis distance between a non-classified register as the black one in a cluster to every observation in a classified group of the cluster. For example, YSO, T-Tauri, and BY Dra. After we have those mean distances, we can perform a submean function in order to assign probabilities. And the closer the point is to a subset, means that it is more probable to belong to that subset. So I'm going to present to you right now the results. And following this process, we can self-assign a class to a non-classified source depending on the non-classes of its classes. So we have a probabilistic output, and we could rebuild some interesting classifications from our output. For example, here we have this source that we found in the first cluster, and this source is classified as BY Dragonis star. And we can see, for example, here the probabilities of the most predominant for the most predominant classes in the cluster. For example, we have BY Dragonis, Candida YSO, Orion B stars, T-Tauri stars, YSOs, and we could see that by our model we could find that it is very probable that this particular source is a BY Dragonis star. And when we see it in for example, in ESA sky, we could find that it is actually located in the Orion Nebula, which is a star formation known place. And other sources, for example, we have other sources like this one in the cluster 5, which is classified as a Cipher-2 galaxy. We can see here that it is very probable from our model that this model is classified as a Cipher-2 galaxy. And when we look for it in the ESA sky, we could find that it is actually in the center of the Perseus cluster, which is a non-galaxy cluster. So this is saying to us that this is a galaxy, but it is a specific kind of galaxy. So that's very interesting. That's a very interesting output of our model. So for each source observation that does not have an assigned class, we will provide a probability over classes. We have just shown you just 2 examples of those sources that we want to classify, and this will be the main output of our algorithm. So in conclusion, we have demonstrated an unsupervised approach for the classification of X-ray sources. We use both K-means and Gaussian mixtures. We assign probabilities by a defined distance metric and pipeline. In this case, we assigned those distances by the Mahalanobis metric, and then we use the submean function. We find that this analysis is consistent in expectations in terms of the cluster membership. We have found that they are separated, the clusters are very well separated by the physical properties of the catalog. And we want to present, and we will present, a full list of classes for all the X-ray sources in the Chandra catalog too that don't have currently an assigned class. In the future work, we want to cross-match or Chandra source catalog sources with the SDSS optical information, and maybe we will add that optical information to our pipeline. But we want to explore the possibility of performing semi-supervised techniques when we have those optical information, because those optical information could give us more information about the classes of known sources. We want, of course, to do an analysis of typical observations that were misclassified because the model is not perfect, and we have found other sources that were actually in places that doesn't make too much of a sense of the classes that they were provided. So that's kind of it. Thank you, and I will be open for questions.
Thank you so much for your talk. I first need to apologize. Unfortunately, I gave my 2-minute warning a little too early when you really still had 7 minutes left. I think you realized that.
Yeah, I was.
Sorry about that.
Don't worry.
Sorry about that. So a question by Johannes Buchner. He says, nice approach. Do you use observation about how the observation was taken? For example, the exposure depths or the galactic latitude? And would it be worthwhile, in addition to that, would it be worthwhile to use the spectral fits, which may be more stable than the hardness ratios? Because the Chandra source catalog has spectral properties fitted to it too.
Thank you. Let me read again the questions. Was taken. Information about how the observation was taken. So yeah, well, we are using just the information about the source specifically, like actually I shown all the properties that we use in our method here, and those are more related with variability, with the spectroscopical measurements, and for example the hardness ratios. We have some properties related to the strength and the temperature too. But yeah, to my knowledge, we don't have use information about how the observation was taken. For example, the lifetime. We haven't used that yet.
Sounds reasonable to me, since there's clearly going to be a bias in how people write certain proposals. Right? Oleg Kagaltsev asked in the Slack, he says, it's a nice talk and interesting approach, Victor. What do you think is the main advantage of your unsupervised approach in comparison to the supervised approaches that people have discovered, that people have discussed in the previous talks? What's better? What's worse using unsupervised versus supervised methods?
Well, yeah, but as I said here, we have many challenges to overcome in supervised learning. And it's very interesting that, for example, we provided here probabilistic classes without having a training set. And that is something that we kind of are grateful of, because we didn't have to we didn't have to construct the training set for classification. And what we are doing on supervised approaches, we could, for example, we could use just the X-ray information that we have here. And that's very interesting, because when we are doing, for example, supervised classification, we need cross matches with sources that have actually classes. So I think that it is a kind of a good point from the unsupervised classification and unsupervised approach, that we don't have a training set, we don't need a training set, and we can perform the model with all the sources that we have provided, that we have this available in the Chandra source catalog. Did I answer the question?
Sounds good to me. If not, the person who asked, you can always post a follow-up question on Slack and start a thread there.
Of course.
A question by Hui Yang on Slack. Do you have any comments on the accuracies or inaccuracies of the Simbad classification? That's something that I've myself seen before. Like you have these ONC stars, you had the YSOs, you have T-Taris, which are kind of almost the same thing, except that for some reason Simbad thinks they're different classes. And I'm sure that happens in other fields too. Do you have any comments on what that should?
Yeah. Yeah, they give multiple classification for the same source. Thank you, Huyan. Thank you for putting that in the table. We have taken mostly the main type that is classified in Simbad database, and we haven't actually analyzed a lot about the accuracy of those classifications. And for example, but we have known that those classifications, and most of them are not very, or a lot of them are not very good. For example, we have ambiguous classifications, as I say here, and those ambiguous classifications, we want to provide a probabilistic classification to them based on our method. For example, we have the X-ray source classification. We have the unknown classification too. And yeah, you could find that actually here in the tables that I presented. So we have, for example, the star, that is a kind of an ambiguous classification from the Simbad database, but we are taking on account those classifications. We are taking on account those sources that classified as that, because we find that an ambiguous classification, and we want to have a probabilistic assignment by our method.
A similar question that just came in on the Zoom is, do you find any source types that you essentially see in every cluster? So the things are that you can't really classify, that turn up everywhere, and that just don't cluster very well in the parameter space that you're using?
You mean the question from Solen Ballman?
Yeah.
Okay. I think that I don't get your question very good.
Well, let's say there is some type, let's say QSO. It's probably not that, but that turns up in all 6 clusters. Do you have anything like that? Anything that turns up in every cluster, essentially?
Yeah, of course. We have many sources, many kind of sources that appear in very other clusters. For example, we have YSOs appear in most of the clusters. So those are very interesting. But what we are trying to do is we know that we have contamination in our clusters, of course, and we have classes that are contaminated in our clusters. But for that, we are taking the most prominent classes in our cluster. And for example, in the cluster 1, for example, in the cluster 0, we have Orion B stars, YSOs, Theta stars. But then if you go down, you will find high mass secondary binaries. But we are taking this cluster, for example, taking just the 5 most prominent classes, and in order to say that this cluster is dominated by, for example, joint stars.
Thanks a lot. That was an interesting talk and a good answers to all of these things. I've seen that there's some of the questions have sparked further discussion, and there's going to be some talk going on Slack, which of course all of you can continue after the Zoom session closes. I want to thank all of the speakers in this session again, including Víctor and all the previous speakers. We have the next session in about 30 minutes at 12 o'clock Eastern time using the same Zoom link. And we welcome everyone to come back to that. I want to announce one more thing. We've been asked to provide, or if we have a more social meeting place, like in a normal conference, you would now walk out and get your coffee or get your lunch and run into other people. So we've set up 2 rooms on Mozilla Hubs. The link is on the Slack and the general channel, where you will walk around or can walk around with an avatar in 3D through like a hall or on a beach or something, and just ran into people and chat. Some more instructions are on there. Each room holds up to 25 people, but we only have 50 people listening right now. So if you can't get into one, just try the other link. If one is empty, just try the other link. Maybe everybody's congregating in the other one. Those rooms are open 24/7. So you can join them now for your coffee, or maybe just before or after a session, we probably have the highest chance of running into anybody. If you have any technical problems with that or questions, I added a coffee channel to the Slack that I'll try to monitor and answer questions. And then here on Zoom, we'll see you back in 28 minutes. Thanks a lot, everybody, for listening and for talking.